nanohub.org.
Okay, so today is the third lecture in the course, and the topic is advanced topics or additional topics in scanning tunneling microscopy. So this will be the last lecture devoted to STM. The next lecture will make a transition from scanning tunneling microscopy to atomic force microscopy, and then we'll start to talk about atomic forces between a tip and a substrate. But before we get there, I just wanted to review a few important topics, things that are interesting in the world of scanning tunneling microscopes. And the agenda for today is to discuss a little bit about this scanning tunneling spectroscopy, this current imaging tunneling spectroscopy, so-called CITS. Right? Both of these techniques are designed to give you local information, local electronic information about substrates. They're inherently an electrical technique. We also want to talk about the barrier height, and we want to talk about measurements of that barrier height, how accurate it can be measured. I want to talk a little bit about forces on a tip. This will start to set up the AFM discussion in another week or so. We'll talk about how high is an atom, right? That's referred to as atomic corrugation. And then the last topic will be just a brief discussion of this quantum corral that has gotten a lot of attention in the last few years. So this is basically a review of how a scanning tunneling microscope works. You recall, if there's no bias, if there's no voltage between the tip and the substrate, and if the tip is brought to within a nanometer or so of the substrate, then there's a approximately square potential barrier. The width of that barrier is d. There are electrons on either side of the barrier. They are prevented from flowing from the tip to the substrate or vice versa by the presence of this work function barrier, this parameter we call phi sub barrier in this diagram off to the left. Because electrons are fermions, they obey Fermi-Dirac statistics, all the electron states in the tip and the substrate are filled up to a characteristic energy which is referred to as the Fermi level, E sub f. That's shown as a solid red line in this diagram. All the energy states below E sub f are filled. All the energy states above E sub f are empty. That statement is rigorously true at 0 degrees Kelvin. When you have a tip and a substrate that are, let's say, at room temperature, there's a small smearing of that Fermi level. And there are some states above the Fermi level that are filled, and there are some states below the Fermi level that are empty. But for the purposes of this talk, we're going to pretend like the Fermi level is a sharp demarcation between the filled and the unfilled states. The question becomes, what happens if you apply a voltage to the tip? Now, when you read the literature, it's important for you to be sensitive to the fact that the voltage could be applied either to the tip or the substrate. And it's up to the author of the paper to tell you where the voltage is applied with respect to. Very often this is a confusing feature when you're trying to sort out some of these published works. But in this case, we're going to take the substrate is grounded. We're going to apply a negative voltage to the tip, and we then have the situation that's shown in the upper right panel of this slide. The negative voltage applied to the tip causes an electric field to set up between the tip and the substrate. In addition, that negative voltage raises the Fermi level of the tip with respect to the substrate. And now all the electrons that are enclosed in that blue shaded box, all those electrons can quantum tunnel through the barrier of finite width and move into the substrate. So there's actually a tunnel current that's set up between the tip and the substrate if you apply a negative voltage to the tip. The tunnel current is dominated by electrons at the top of the Fermi energy, near the Fermi energy of the tip. That's indicated by the dark black arrow. As you go down in energy, right, the transmission probability decreases. And so the contribution of the tunnel current to electron states that are, let's say, an EV below the Fermi level of the tip, that contribution is diminished. It just depends on how far down you actually go in energy. And that, of course, is adjustable because you can apply any bias voltage you want to the tip, right? The bias voltage can be a millivolt or 1 volt. That's experimentally under your control. The tunnel current flows, okay? It should be clear. The tunnel current flows because the states on the left of the barrier are filled. They're below the Fermi level. The states that they tunnel into on the right are above the Fermi level, so those states are empty, right? And so electrons, you can't put more than 2 electrons in a given state. And so if you want to, into a given quantum state, so if you want to set up a tunnel current, you want electrons to go from quantum states on the left of the barrier to quantum states on the right of the barrier. You have to make sure that the states on the right of the barrier are empty, or otherwise the electrons won't go. Okay? So that, for instance, is why there's no tunnel current below that blue band. Right? In principle, those electrons could tunnel from the tip to the substrate, but if they do so, they'll tunnel into filled states that are already filled. And because they're filled, they can't accept any more electrons. And for that reason, the tunnel current ends abruptly at the bottom of that blue box. There's nothing sacred about a negative applied voltage. You can apply a positive applied voltage. If you apply a positive applied voltage, then what you do is you just reverse the polarity of everything I just said. Right? Now electrons will tunnel from the substrate to the tip. Again, the electrons at the top of the Fermi level of the substrate, those will tunnel with the highest transmission probability. And as you move down in energy, the arrows that decrease in intensity indicate schematically that the tunnel current at those energies is reduced. Okay, so this scanning tunneling spectroscopy, this STS, uses this effect of applying a bias voltage between the tip and the substrate, rastering the bias voltage in a systematic way, and just measuring the tunnel current that flows. And in the process of doing that, you actually learn something about the filled and unfilled states of the substrate. Okay? The first situation when you're tunneling into unfilled states, you're mapping out how many electron states there are versus energy that are unfilled. In the bottom case on the bottom right of this slide, when you reverse the polarity of the bias, right, you're actually probing the filled states of the substrate, within EV of the Fermi level, okay? So it's a very clever way to sort out how many electron states are filled, how many electron states are empty, right? Now, what determines the electron flow in more detail? Basically, again, I'll write down an equation, I'm going to justify it, I won't derive it. The total tunnel current that flows is a constant. It's 4 pi times the electronic charge divided by Planck's constant, h bar, times an integral over all energies, right? From minus infinity to positive infinity. That integral has 4 terms that are noteworthy, okay? So let's start at the end and work backwards. The term that's labeled T of epsilon and V, that's the transmission probability that an electron will tunnel through that barrier at a certain energy E, or a certain energy epsilon, for a certain applied voltage V, right? So the first homework set in this course gives you some experience in calculating this transmission probability for a square barrier for different energies, right? And you'll see that that transmission probability varies exponentially, right, with energy to a very good approximation, right? So the transmission probability at the Fermi level could be small. It could be 10 to the minus 6, 10 to the minus 7. But as you go down in energy, the transmission probability decreases rather rapidly. And so all the tunnel current is basically carried by the electrons indicated by that dark arrow inside the tunnel barrier, that energy. Right? The electrons at that energy carry the dominant part of the tunnel current. But nonetheless, if you want to do an exact calculation, you have to integrate overall energies, and that's what this equation says. So you got to know that the transmission probability T. There are two density of states terms. These are local density of states. These tell you how many electrons are available at a particular energy epsilon. There's a density of states of the substrate and a density of states of the tip. And these two density of states are offset one by another simply by the bias voltage that we apply. That's EV. It's the voltage applied to the, in other words, it takes into account the fact that the Fermi level of the substrate has been shifted down by applying this minus voltage to the tip. Right? So we have to, in principle, know those things if we want to make an absolute calculation of the tunnel current. In practice, what we want to do is we want to measure the tunnel current and infer something about density of states. So we want to work backwards. And I'll show you how that comes about. The term in the square brackets is the difference in the Fermi function between the electrons on the left and electrons to the right of the barrier, right? So this Fermi function is a well-known function in condensed matter physics. I just make a plot of it here, just so we can discuss it in more detail. It basically varies between 1 and 0, and it tells you the probability of occupation that a certain electron state will have as a function of energy with respect to the Fermi energy, right? So at very low temperatures, like 5 degrees Kelvin, right, that Fermi function is a sharp step. It's a very distinct step function. As the temperature increases, the Fermi function spreads out, and you can see I did calculations for 1,000 and 5,000 Kelvin. You can start to see that 5,000 Kelvin, that step function gets broadened into a gentle step that now varies significantly over a few EV in energy. At 300 Kelvin, right, that step is about 0.025 electron volts wide. Okay, so if you just plug in room temperature, which is about 300 Kelvin, into that function in the top and evaluate it, evaluate Fermi-Dirac function, you'll find that it's not such a sharp step as 5 Kelvin, but it's still pretty sharp, right? And so to a very good approximation, when we take data at room temperature, right, we just approximate this Fermi-Dirac function as a step function, which is 1 below the Fermi energy and 0 above, right? Now, the reason I mention that is because this term in the square brackets in this equation is the difference in the Fermi function between the tip and the substrate, okay? And if you work that out, it's just the difference in two step functions. One step function is shifted with respect to the other. And basically what it says is that in the region which is indicated by the blue shadowed box, right, that term in square brackets is unity. And outside that region in energy, indicated by that square blue box, the difference in the Fermi functions is 0, right? So what that means is that integral from minus infinity to infinity over all energies can be now approximated by an integral just over the region of energies given by this EV that's shown on the right. So only the electrons between the Fermi energy of the tip and the Fermi energy of the substrate contribute to the tunnel current. And we can simplify that integral quite nicely. We don't have to go over all energies anymore. Okay? So those are the 4 features that determine, in principle, the tunnel current in any STM experiment. Okay? It's hard to evaluate rho sub tip. It's hard to evaluate rho sub substrate. Instead, what we do is we make some simple approximations and we try to infer the density of states on the substrate from measurements of the tunnel current. And that's what I'll like to illustrate in the next slide. Okay. So if we make the measurements at room temperature or below, right, the smearing of the Fermi-Dirac distribution function is only about 0.025 electron volts, which is pretty small. So that means that if we restrict our attention to voltage bias swings between the tip and the substrate, much greater than 0.025 volts, right, we can well approximate the Fermi function as a step. Right, so typically experiments are done by sweeping a bias voltage between, let's say, minus 500 and 500 millivolts. That's about 20 times KT, so it's a reasonably good approximation. There's a question.
Is the Fermi energy of the tip and the substrate almost equal, or how different are they?
Well, in this discussion, we're pretending that the Fermi energy of the tip and the substrate are the same. Okay? That's not always the case. And what happens is when you set up this tunnel junction at zero bias, at zero voltage, there will be a certain amount of current that flows one way or the other to initially shift the Fermi levels of the tip and substrate so that they are the same. The way that happens is charge actually will transfer from either the substrate to the tip or the tip to the substrate. And in the process of transferring, the Fermi levels will realign. Okay? The net result is the square barrier that we assume between the tip and the substrate is now no longer square. There's an internal electric field that sets up between the tip and the substrate. And that just causes a complication of in describing the detailed shape of that barrier. In reality, we don't know what that barrier looks like. I'll tell you honestly up front right now. We approximate it as a square step, but we have no way of measuring it experimentally. We can measure certain things. We can measure certain quantities, and I'll describe that in a few minutes. And I can show you that the height of the barrier that we get out is reasonable compared to work functions of well-known metals, right? But in all honesty, we don't really have a very detailed equation to describe that barrier shape. Okay. So the first equation on this slide, right, takes into account the fact that the Fermi-Dirac distribution function can be approximated as a sharp step. And the net result is that integral from minus infinity to infinity now just spans the range of the bias voltage V that we apply between the tip and the substrate. So you can see the integral limits have changed. In addition, we have made the assumption that the density of states of the tip doesn't change a whole lot with energy, right? And we pull that out of the integral. So we say density of states of the tip is a constant. We can pull it out of the integral. And we also can approximate this transmission probability, which again is difficult to calculate for a realistic barrier. We can approximate that by some average transmission probability T, and we can pull that out of the integral also. So with some reasonable approximation, the tunnel current that flows now is just an integral of the density of states of the substrate over the range in energy that's specified by the bias voltage that we apply. Okay? And it follows from the second equation on this slide that if we could take the derivative of the current with respect to the voltage, right, we basically undo that integral and we are left with an expression that has a bunch of constants that we don't really know. times a quantity which is proportional to the density of states of the substrate at the bias voltage that we apply, right? So to a very good approximation, what we're saying is that the derivative of the current with respect to applied voltage, if we can somehow measure that quantity or evaluate it, right, we actually have a quantity now that's proportional to the density of states of the substrate. And that is the end goal of STS, scanning tunneling spectroscopy. It's to measure something that's proportional to the density of states of the substrate. Right. So how is the experiment actually done? Well, we tried to introduce this idea that if you move the tip across the substrate in a rastered way, in a controlled way, right, all the while maintaining a constant tunnel current, we tried to convince you that experiment allows you to infer the topography of the substrate, right? So you have this very sensitive height monitor because you're scanning the tip and maintaining a constant tunnel current. And in the process of scanning the tip and maintaining a constant tunnel current, you've got to move the tip up and down, and the tip moves up and down in just the right amount to mimic the geographic, the topographic features on the substrate. Right? So if you measure how much the tip moves up and down, let's say each grid point in the substrate, the grid points are specified by these crosshatched lines in this diagram, you get a very nice topographical image, which allows you to see atoms, okay? But if in addition, at each point that you do a topographic measurement, you now ramp the voltage and measure the tunnel current, right? You start to do a scanning tunneling spectroscopy experiment at every point in your image, right? And this is referred to in the literature as a current imaging tunneling spectroscopy, a CITS. And it basically means that you got one image which is topographical, and then you've got another image which is basically how the current varies as a function of applied voltage at every point on your substrate. Okay, now why would you want to do that? Well, because if you pick out a particular bias voltage, in this case I indicate, let's say, 6 bias voltages indicated by those black dots, right? So those are somehow preset bias voltages that I'm very interested in. If I can measure the slope of the current voltage curve at each of those 6 data points, then, according to the discussion on the previous slide, I am measuring something that's proportional to the density of states of the substrate, because dI/dV is proportional density of states of the substrate to a good approximation, right? And so that is the important quantity that we want to get out of this. We want to measure at preset bias voltages. These preset bias voltages are something that the user could then specify. We want to measure basically the slope of the IV curve at every bias voltage, and then therefore infer what the density of states of the substrate is at each of those voltages. So on paper, this sounds like a great technique. The problem is it's time consuming, right? If you have to sweep out an IV curve at each data point, right, you're going to extend the length of a measurement by factors of 2 or 3 beyond which you just acquire the topographic image. So for instance, a typical topographic image has 256 by 256 data points, right? If in addition you want to do an IV curve at each of those 256 by 256 data points, you're going to get a massive amount of data, right? And it's going to take a long time to acquire all that data. So very often you'll take a topographic image, let's say with a resolution of 256 by 256, but maybe you'll only do 64 by 64 CITS scan to cut down the time it takes. So you're limiting the information that you get from the CITS data by restricting the number of data points that you perform IV curves as you scan the topography. So software packages now have all that built in where you can specify how many CITS data points you want. You don't have to take a data point at every pixel in the image, right? But even so, if you reduce the number of IV curves by, let's say, a factor of 10 below the number of pixels in your image, you still have tens of minutes to acquire a CITS image. And that means there's a significant drift, right? There will usually be a significant drift between the start of your image and the end of your image, right? And so the image, unless your microscope is drift compensated, right, you'll sort of lose track of where you're at in the process of performing the CITS measurement. So it's for this reason that people use low temperature scanning tunneling microscopes. They go to 4 Kelvin. Because if you go to 4 Kelvin, right, the thermal drift essentially disappears. You can start a CITS image at 5 o'clock at night, and you can let it run all night and come back the next morning, and the tip is drifted in a absolute sense by just a fraction of an angstrom from where it was at the beginning, right? So most of the CITS data, most of it is done at low temperatures in order to eliminate the thermal drift. Okay, yes?
Can I ask a question? I mean, this correlation between DIDV and density of states is, or at least theoretically, it's sort of developed for a constant error where the gap is a fixed number. So for a fixed gap, you ramp which is V. I wonder in the CITS thing, you know, as you go point to point, you got to keep the gap constant and change the voltage. That seems like a hard thing to do.
Yeah.
You know, and how do you choose what gap to do this at? What are the implications?
So the question basically involves whether this transmission function t can be brought outside the integral, right, and replaced by some average value of t. And the answer is, of course not, it can't. But it's very hard to evaluate the transmission unless someone tells you what the exact shape of the barrier is. And we don't know the exact shape, so we're left with these crude approximations. It turns out there are ways that have been developed to minimize the influence of the variation of the transmission probability with voltage, right? And there are techniques that are published in the literature which allow you to try to divide that out, that variation in t, out to a first approximation. But in reality, all you're looking for is whether, you know, it's hard to make quantitative estimates. You can say the density of states goes up or it goes down with voltage, but you can say maybe it goes up by a factor of 2 or it decreases by a factor of 2, but you can't get too much more detail than that. Well, people do it, but I don't know how believable it is, right? People do all kinds of things. But yeah, it's that taking t out of the integral is a big approximation. How do you actually make the experiment work, right? You have to think about this because this experiment is not the same as taking an image, right? What you basically have to do in the process of a CITS experiment is you have to turn off your feedback loop. And the reason you have to turn off your feedback loop is because the current is not going to vary as you ramp the voltage, right? In fact, the current's going to change polarity. If you change the polarity of the voltage, the current will change polarity. Right? Now, the feedback loop is, of course, designed to keep the tip at a fixed distance above the substrate. So if the current starts to vary and the feedback loop is on, feedback loop is going to start to do some really crazy things to try to maintain a constant tunnel current. So the first thing you have to do is you have to turn off the feedback loop, and that's what's indicated in the top panel of this slide. After the feedback loop has been turned off, you then have to ramp the bias voltage in a smooth way from some initial bias to some final bias. So from minus V to plus V. And while you're ramping the bias voltage, right, you then have to measure the tunnel current. In particular, there's usually a preset number of voltage points where you measure the tunnel current. And then from this IV curve, after it's been accumulated, you then have to take a derivative, and you have to evaluate the slope of the IV curve at different points indicated schematically by those solid dots on this curve. Right? This is all at one pixel. This is all at one XY position of the tip above the substrate. You have to repeat this process as you raster the tip in a systematic way over the sample. Right? You constantly have to be turning the feedback on and off, ramping the voltage, measuring the tunnel current. So clearly, if there's a big drift in the tip when you turn the feedback off, if the tip approaches the substrate or pulls away from the substrate, then your measurement of IV is meaningless. Right? The implication is that when you turn the feedback off, the tip stays at a fixed position above the substrate. This allows you then to ramp the voltage in a controlled way, measure the tunnel current. But if the tip is drifting in or out after the feedback loop is off, this is tough. This is very hard to deal with. Right? So it's a beautiful measurement, but it requires a lot of care to ensure that you do it correctly. What does the typical data look like from a CITS measurement? And I just show this sequence of images that I obtained from the Omicron website, right? What you can see is each image is taken at a different bias voltage, right? So each image corresponds to one of the black dots on the IV curve that I showed previously. And the important thing for you to recognize is that the images vary as the bias voltages change, right? So that's the take-home message. Right, if every image looked exactly the same, then this wouldn't be interesting. But the fact that the images taken at, let's say, plus 2 volts looks different than the images taken at minus 2 volts is telling you something about how the local density of states on the silicon surface varies as the bias voltage or as the energy of the electrons is swept over the plus 2 to minus 2 volt range. Right? So this is a typical output from a CITS image, right? It's a sequence of images, each image taken at a different bias voltage. And then theorists will go in and they'll try to interpret the details of the image by calculating local density of states and trying to compare their calculations to experiment. Okay, so they try to reproduce these images from first principles theory. Okay? Yeah.
Silicon 7x7 reconstructed surface is metallic. How do one can get the band structure for this reoriented surface?
So silicon 111 surface is metallic.
It's 7x7 reconstructed surface. How do through STS studies how can one can derive the band structure?
So the band structure, by the band structure, I assume you mean the amount of doping that occurs,
No.
right? The band gap is 1.2 eV for silicon, right? So, I mean, if that's what you mean by band structure, right, then basically the IV curve will be reasonably flat around V equals 0 by plus minus 0.6 volts, right? That'll reproduce the band gap in silicon. Right? So if you see the current is suppressed near V equals 0, of course when V equals 0, there's no current that flows. But if there's a true band gap in silicon, right, as you bias the tip with respect to the substrate, no current should flow until you hit either the conduction band or the valence band edge. And that's when the tunnel current would pick up and start to increase above I equals 0 on this diagram. So the crude band structure can be inferred by just looking at how flat the current is over what bias voltage range, right? And then you can infer from that a band gap, if that's what you mean by band structure, right? I wanted to say something about the apparent tunnel barrier height, this parameter phi that appears in all this discussion of scanning telling microscopy. That's a very important parameter because if you think about it, that phi subbarrier quantity determines the attenuation coefficient alpha that determines the exponential dependence of the tunnel current with position z. Right? And so if you want to know how rapidly the tunnel current falls off as the distance between the tip and the substrate is varied, you've got to make a measurement of that barrier height phi. So there's a standard way to do that, and since the current varies exponentially with position z, the logical thing to do would be to take the natural logarithm of both sides of that expression I equals I naught e to the minus 2 alpha z, right? So if the work function, if the barrier height is measured in joules, and if the position z is measured in meters, right, then that equation is consistent. But usually we measure z in angstroms, and we measure work function barriers in electron volts. Right? So if you want to convert that equation from the standard SI set of units into a more convenient set of units, you have to change the units, and I indicate how you do that by the two numbers in red. And what you can find is that this constant that now multiplies z in this special set of units where z is in angstroms, the work function barriers in electron volt, that constant turns out to be 1.029, right? So you'll see that 1.029 in the literature all the time. They rewrite the top equation, I equals I naught e to the minus 1.029 times z, where z is, or times the square root of the barrier in electron volts times z in angstroms. Okay, now why do we do this? Well, we do this because it follows that if you take the derivative of the natural log of the current with respect to z, right, if you just take the derivative of the fifth line on that slide, and you square it, right, you square it, you'll find out that that derivative is equal to this constant 1.029 times the barrier height in electron volts. And so if you're in the business of trying to measure the exact value of that barrier height, the way to do it is to measure how the current varies with z, take the slope of that, the derivative of the natural log of I with respect to z, square it, right? Divide by this 1.029 and you'll end up with an expression on the bottom which tells you what the barrier height in electron volts is. So this was a big issue in the early days of STM. Right? Everyone realized that this simple square barrier was an approximation, but the issue was how crude of an approximation was it? So lots of people tried to measure barrier heights, right? So what you should know is that most barriers for metals, for refractory metals, most barriers are on the order of 4.5 to 5.5 electron volts. So you would expect that barrier heights coming out of this measurement would be somewhere on the order of 4 to 5 eV. In practice, the numbers that we were all getting at the time was closer to 1 EV, right? It was about a factor of 4 or 5 lower than what we expected. And the question was, you know, is this square barrier approximation that bad that it causes you to miss the height of the barrier by a factor of 4 or 5? Right, so that was a big puzzle, right? Person that first explained to me the nature of the problem was Fleming Biesenbacher. he published a very nice paper in 1996, and I referred to that paper here. What he did is he very carefully measured the variation in the tunnel current as you change the position between the tip and the substrate. He made the measurements in ultra-high vacuum. He took extreme care to clean the tip. He took extreme care to clean the substrate, right? And when he did these, when he took all kinds of precautions in making sure that his tip was clean and the substrate was clean, he actually found a tunnel current that did in fact vary exponentially with displacement of the tip and the substrate. That's indicated in the middle panel of this data slide on the left. And then if you apply that simple analysis that I sketched out on the previous slide, you can back out work functions or heights of barriers. And the heights of the barriers that he quotes in this 1996 paper, these heights are very, very consistent with what you would expect from your prior knowledge of work functions of metals. Right? So he showed very nicely that if you take extreme caution and exercise all due diligence, that in fact the barrier heights that determine the tunnel current variation with Z, those barrier heights do in fact come close to matching the work functions of elements that have been known in the literature for 100 years, right? So his paper was, I don't know if it was the first to show this clearly, but it was certainly a revelation to me that you had to be very, very careful about cleanliness of both tip and substrate if you want to do careful STM measurements. So I wanted to just mention that these barrier heights are reasonable. They can be a lot lower if there's contamination between your tip and the substrate. And most of us that were trying to make the measurements, we were trying to make the measurements in a clean environment, which meant dry nitrogen, right? But that's not the same as ultra-high vacuum, right? And we did not go through nearly the cleaning techniques that Biesenbacher's group introduced in order to make these measurements. So our measurements were much lower for barrier heights than his. Another issue that's kind of important and sort of sets the stage for atomic force microscopy is to ask the question, what's the force of the lead atom on the tip? Right? So, you know, all the early STM work, everybody's very excited because you can get these very beautiful images and you can start to see individual atoms, but then you start to ask yourself, well, why does it work? Because the bias voltage that you apply between the tip and the substrate, that bias voltage could be, let's say, a volt. And if the tip and the substrate are separated by a nanometer, then there's an electric field that's 1 volt per nanometer. That's about 10 to the 9th volts per meter. Well, I don't think any of you have seen 10 to the 9th volts per meter in your life, right? If you go out in Indiana in the summer in a cornfield when there's a big thundercloud, maybe you'll see 10 to the 7th volts per meter. The electric field between the thundercloud and the earth is on the order of 10 to the 7th volts per meter. That's enough to make your hair stand on end, right? But 10 to the 9th volts per meter is a factor of 100 higher. And those fields they can be achieved in the laboratory environment, but they're strong enough to actually rip atoms off the tip, right? They just field desorb. The electric field is so high enough that it desorbs atoms from the tip. So just simple considerations, back of the envelope arguments would say that these tunnel junctions should be unstable when your bias voltage starts to approach a volt or so. And in fact, anybody that's done STM will tell you that if you put too high of a bias voltage on your tip, your tunneling current goes crazy, right? It's very hard to control a constant tunnel current, presumably because the tip atoms are getting ripped off and moved around, okay? But nonetheless, it's an important question to try to answer. And question is, how would you measure those forces? And so there were a number of experiments done in the late 1990s, right? And one technique that was used was to put a gold substrate on the back of a floppy microcantilever, right? Now, a microcantilever, if you apply a force to the apex of the cantilever, to the end of the cantilever will bend. And the way it bends is given by these standard equations from mechanics, and these equations will be derived in more detail as we move into the AFM part of the course. But the bottom line is that if you tell me what the spring constant of the cantilever is, K, in newtons per meter, if you tell me the length of the cantilever, L, and if I measure the deflection angle of the cantilever, theta, then I can calculate what the force is exerted on the cantilever to cause it to bend through that angle theta. So it's just 2/3 KL theta. That's the bottom line. So the idea is real simple, right? If you want to measure the force that the tip exerts on the substrate, right, you evaporate a thin conducting layer of material on the back of the cantilever. You slowly bring the tip down, and you monitor the deflection of the cantilever. And the deflection of the cantilever is proportional to the force between the tip and the substrate, and the proportionality constant is just 2/3 KL, which those are numbers that you know. All right? So that was the idea on how to measure these forces. Very nice measurement in this regard was done in 1998. It was a collaboration between Durig's group in Switzerland and Gruder's group in McGill University in Canada. And I just wanted to show you the results of an experiment that they performed using this cantilever as I described previously. What you're seeing in this plot is the tip sample separation in nanometers. There's an arbitrary 0 in the x-axis because it's hard to know precisely where the tip sample contact is, right? It's very hard to establish z equal to 0 in any of these scanning probe studies. So they've arbitrarily established a 0, and then they varied the tip sample separation by a nanometer about that arbitrary 0 position. So they've moved it in a nanometer and they've retracted it a nanometer. And all the while they're pushing and pulling in, right? They're measuring the deflection of the cantilever. And then from the deflection of the cantilever, they can infer in absolute values, right? Absolute force values, what the force of the tip is on the substrate. And so that's labeled on the left, right? And what they found was that as they moved the tip closer to the substrate, right? First there was an attractive force, caused the cantilever to bend towards the tip. That's represented in this diagram by negative force values. And then as they continued to push the tip in closer, the cantilever actually deflected away. That's represented by positive force values on this graph. So there's a repulsive and attractive regime, right? They actually mapped out very crudely what the shape of the force versus distance curve looks like using scanning and tunneling microscopy. Okay, that was 1998. Gruder's group came back in 2005 and did the measurement much more carefully, and I show that data here. Right, same idea of using a cantilever. It's just they got much wider range of currents now, and their tip sample separation is controlled a little bit more precisely. Right, the important graph on this slide is the data in the far right panel of the force versus tip sample separation. Right. What you see is that as you approach, as the tip approaches the gold substrate, right, the current goes up roughly exponentially. It's a straight line behavior. Anytime you see a straight line behavior on a log plot of the current versus tip sample separation, that means there's an exponential dependence of the tunnel current with position, and that should be familiar to you by now, right? what they found is that the tunnel current increased until they got to this point that they call zero. It's an arbitrary zero. Then the tunnel current saturates beyond that. It doesn't change. And that indicates that the tip is now in contact with the substrate, right? And you actually have you no longer have a tunnel junction anymore. You're not tunneling because the current no longer depends exponentially on separation. You actually now have a physical contact between the tip and the substrate. And what's interesting is when you retract the tip, you pull it out, you can see that that tunnel current is maintained at a constant value for about 3/10 of a nanometer, right? So how can that be, right? How can that be? What they're saying is the tip comes in, right? The tunnel current increases. Finally, you make contact with the tip. You push the tip, right? Then you start to pull the tip away, and the tunnel current stays at the same value for about 0.4 nanometers. Well, that's an indication of adhesion. That means that the tip is actually stuck to the substrate. There's an adhesive force that maintains this tip substrate contact. You can see it stays flat, and then finally the cantilever snaps loose, and then the tunnel current starts to decrease exponentially with distance, as you would expect, right? And from this data, again, they were able to infer forces because they were measuring the deflection of the cantilever, the angle of the cantilever as it deflected. They monitored that very accurately. And the forces they were getting were on the order of 10 nanonewtons or so, right? And the force distance curve, there's a bunch of data points. You have to look at the original publication to sort it out. But you can see that the force distance curve is hysteretic. Right? You get a different value coming in and going out. And of course, that difference is because the tip is physically stuck to the substrate. There's actually a neck of atoms that forms between the tip and the substrate when the tip physically touches the substrate. So this is one of the early measurements done to try to sort out forces, acting on atoms in, tips, forces on atoms acting on substrates. There are various models that have been developed, and I just wanted to call your attention to one model. This is from Julian Chen's nice book on scanning tunneling microscopy, where he actually calculates the displacement of tip atoms and substrate atoms as the apparent distance from between the tip and the sample is varied. Right? So you can see that when the tip sample distance is large, on the order of 0.6 nanometers, there's very little displacement between the tip and the substrate, or between the gold substrate atom and the tungsten tip atom. But as the tip gets closer to the substrate, right, the dash curve indicates that the front atom on the gold surface actually pulls toward the tip. Right? It humps up there. It goes up by quite a bit, about 40 picometers. The tungsten atom on the tip also approaches the substrate. It relaxes. The relaxation of the tungsten atom is about a half that of gold, because tungsten is certainly a stronger metal than gold, right? And then as you continue to push the tip closer to the substrate, you start to get around separation of about 0.3 nanometers, right? Then, only then do you actually return the gold and tungsten atoms to their original positions. And if you continue to make that distance between tip and substrate shrink, then you actually compress the gold atoms and the tungsten atoms. That's indicated by a negative value for the relaxation of the position of those atoms. So the bottom line is, right, you can believe the calculation or not, right? But the bottom line is that simple models of this tip-substrate junction indicate motion of tip atoms by something on the order of tens of picometers as the tip comes closer to the substrate and as it's pulled away, right? So this will be a limiting factor, right? It's present all the time. It's always there, right? Whether you see it or not is another issue. But the forces between the tip and the substrate are significant, and they can cause tens of picometers of deformation. Easily tens of picometers of separation between, let's say, a tungsten tip and a gold substrate. So that's something you got to remember, especially when we start to talk about AFM in another week, right? That sort of sets the scale for the deformations that could occur. Another topic I wanted to talk about is how high is an atom in scanning tunneling microscopy? It's kind of an interesting question. Everybody in the early days was just excited that you could see atomic periodicity of the substrate atoms with an STM. And there wasn't much care given to understanding the height of the atoms in the STM images. It was more the periodicity that was the big thing. But as the field evolved, then people started to want to know how high is the height of an atom in an STM image. And so the way you answer that question is you obtain, let's say, a high-resolution STM image of a substrate. The particular paper I pulled out is by Wiesendager's group in Germany. They looked at 3 surfaces, tungsten 110, tantalum 110, and iron 110, right? And they measured the atomic corrugation, the ups and downs that the tip registers as it scans over the substrate. So there's you define a line in the image, and then you can plot the height profile along that line. And what you find is that the distance between the peaks and the valleys is on the order of 15 picometers, implying that the height of an atom in an STM image is on the order of 15 picometers or so, right? It's a pretty straightforward measurement. Interestingly enough, they found that this corrugation depended on the applied voltage to the tip, right? So if you change the voltage between the tip and the substrate, this corrugation of the atoms varied, right? Now, this is hard to believe, because you like to believe the size of the atom is independent of the voltage that you apply to a tip, right? So what's going on? Well, the answer is, as you apply a voltage between the tip and the substrate, you're actually measuring different density of states, right? You're actually measuring different wave functions. And these wave functions can have a corrugation that depends on energy. And so that's in fact what they're observing here. So they imaged very carefully a unit cell indicated by this sequence of dots in the bottom right-hand image of this picture, right? The images that they obtained for different bias voltages are pasted as insets into this diagram. And you can see that the corrugation depends on the bias voltage, right? Which is kind of a surprising result. But in reality, it's just a reflection of this local density of states problem that we've sort of been talking about for the last 2 lectures. Okay? Very nice set of data. All right? They went on to explain quantitatively the differences in corrugation by assuming different tip atoms. So I alluded to this about 2 lectures ago, where I said the lead atom on the STM tip can be in different atomic states. Right? These different atomic states correspond to the atomic orbitals that you all learn when you study chemistry in high school. They're referred to in this diagram as the S state, the PZ state, or the D2Z state. And depending on which atom, depending on which state the lead atom on an STM tip is currently in, this diagram is telling you that you will get different corrugations, different apparent heights measured as the STM rasters over a substrate. Okay? So if you try to measure with any precision the height of an atom in an STM image, that's not enough. You got to also know something about the state of the apex atom, that lead atom on the tip. You got to know what quantum state it's in, okay, if you want to make a very precise measurement of this quantity. So I like this because it just emphasizes how detailed this STM, that the information that this thing we call an STM is capable of giving. Right? It really requires a very sophisticated appreciation of the quantum mechanics, how the states from the substrate couple to the states to the tip. Right? Okay? Last topic is a brief discussion of quantum corrals. This is a topic that emerged maybe 4 or 5 years ago, in the early 2000s. It's basically driven by the work at IBM Almaden and Stanford University. And it's just a really beautiful example of the precision that STM can achieve in fabricating structures and then measuring the electronic states that are generated by these fabricated structures. So basically, what is a quantum corral? In five lines or less, quantum corral is some sort of an artificial structure that you construct to confine electrons in a way that they're not normally confined, right? So you have to create some sort of an artificial structure, and that artificial structure has to be efficient at confining electrons. The corrals usually are constructed on atomically flat metallic substrates, right? So the substrate has to be metallic and it has to be flat. The essence of a quantum corral is an electron state that is localized on the surface of the metal. So these are surface states that we're looking at. They're not the bulk electron states that we talked about 2 or 3 lectures ago. But it turns out a lot of the metals have these surface states located on them. And I think the example I'm going to show is a copper surface. So these surface electron states are there. They're states that just run parallel to the surface. They don't propagate into the metal surface. What you do to make a quantum corral is you construct from atoms a fence. Right? You make a fence of atoms, and this fence of atoms is then very efficient at electron scattering. And what the quantum corral demonstrates is that there is a way to transmit information across distances in a metal that does not require wires, right? You can actually just, if you understand it, you can actually use the wave functions of the electrons themselves to transmit information across a distance without the requirement for wire interconnects. So it's a new way of guiding information through solids. And the basic idea is illustrated on the bottom part of this slide. You probably have seen this in your introductory physics classes, right? If you have an incident wave, plane wave, that strikes a scattering center, that incident wave is scattered in an isotropic fashion from that scattering center such that new wavelets are produced at the center of that scattering center. And these new wavelets then emanate from the scattering center in a spherically symmetric way that I've tried to indicate schematically in that diagram. And the idea is if you arrange these scattering centers in intelligent ways, then you can cause constructive or destructive interference of that scattered wave from each scattering center. And this constructive or destructive interference can set up standing wave patterns, right, that persist over, that are independent of time as long as your incident wave is persistent. So that's the basic idea. In this example, the incident wave is basically going to be the electron surface states on a metal surface. And these scattering centers are going to be atoms that are arranged with an STM tip into a pre-described shape. So What you have to realize is that ellipses are special. The shape of an ellipse is very special when you're thinking about scattered waves. And this was demonstrated back in 1825 by some Germans who took an elliptical bowl, filled it with mercury. Right? Now, a property of an ellipse is that there are 2 points in the ellipse called the foci of the ellipse. And if you make a disturbance at one focal point of the ellipse, precisely at the focal point, then that wave disturbance propagates outward, reflects from the boundaries of the ellipse, and is then refocused at the second focal point of the ellipse. And so in 1825, what they did is they took an elliptical bowl, filled it full of mercury, and then they carefully dropped little drops of mercury at one focal point. When that drop of mercury lands on the surface confined in this elliptical pattern, in this elliptical shape, it generates an outward going wave. That outward going wave scatters from the elliptical boundary of the bowl, and it's refocused at the other ellipse. Right? And so if you can imagine dropping a steady stream of mercury drops that fall onto one focus of the ellipse, then at the other focus of the ellipse, you'll find that these wavelets that are generated recombine. Okay? And this is a sketch, right? This is a sketch of what these guys saw in 1825 of this whole phenomenon. Right? You just do it and you can look at it, and if you're a careful drawer, you can make a picture that looks like this. Okay? So the thought is, why not try this with a quantum corral, right? And this result was published in Nature February 2000. This comes out of Eigler's group at IBM Almaden. And what they did is they arranged 36 cobalt atoms to form this elliptical structure. And then they watched how the electron, these surface electron states that are propagating on the copper 111 substrate, how those electron states scatter from that elliptically shaped quantum corral of 36 cobalt atoms. And those ripples that you see in the middle of this image are the constructive and destructive interference of these surface states as they bounce around and reflect off that elliptical shape of the 36 cobalt atoms. And then to mimic the experiments that probably are obvious to everyone by now, they carefully placed another cobalt atom at one focal point of the ellipse, and then they carefully looked, and sure enough, the electron character of the waves that were scattered from that one electron state, from that one cobalt atom placed at the focal point of the ellipse, the character of that electron state was reformed at the other focal point, as indicated by that small purple-colored region, right? So they call this a quantum mirage because there's really no atom present at the focal point on the lower image of this corral. The electron states that are reflected from the atom placed at the focal point in the upper right portion of this corral are reflected from the elliptical shape of the corral and reconverge and form the so-called image of the atom. Okay, so it's a beautiful demonstration. It requires a lot of expertise just to make the corral, and that takes time.
So this is kind of normal topography scanning, right?
I think this is a artist conception of what's going on. If you want the details, okay, if you want the details, you got to look. And I looked at Feide and Heller's paper, Reviews of Modern Physics. They actually worked out the theory and compared the theory to the experiment, right? So first, let's just do the empty corral, the corral without any atoms placed at the focal point. right? So the top image is the topography, right? What you would expect theoretically, taking everything into account that you can possibly take into account. And then on the right is what you would measure experimentally. And you can see those ripples, right? The ripples inside the corral are produced by the surface electron states that are bouncing around inside the corral. And they produce this characteristic ripple pattern. And you can see, you can't see that ripple pattern except if you use STM, right? It's very, very tiny, right? But you can measure it with STM. And you can see that the experiment and theory agrees quite well. And then what's more interesting is if you take make a density of states plot, right? Because experimentally that's what STM is measuring, density of states, right? You measure density of states plots, function of X and Y. Again, you got a theory and an experiment, right, for an empty corral. And what you'll notice is that theory predicts depressions, dark spots at the focal points, and those dark spots in the focal points are actually measured experimentally. So that means there's a deficit of electrons at the focal point of that ellipse when there's no atoms present. Okay? When there's no atoms present. If you then drop an atom in, the situation changes. So again, the top two panels on this slide show the topography, right? So the topography is very clear. The white spot at the focal point is an indication that an atom has actually been placed there. Okay? An atom has actually been placed there now. And it modifies the topography of the interference pattern a little bit. If you go back and forth between this slide and the previous slide, you can see subtle differences in the topography between the two images. But when you look at the density of states, the density of states is now modified enormously. In fact, you can see that hole that was on both sides of the ellipse before, that hole has now disappeared. There's now a high density of states associated with the placement of that atom at the ellipse, and that density of states is then reflected and combined and refocused onto the focal point on the left-hand side. The reconstruction of the density of states is not perfect because there's scattering processes involved in this process, right? The electron states don't live forever, and if they did, then I think you would get an exact mirror image on the left compared to the right. Okay, that's my understanding. So it's a little bit more complicated than this because cobalt is a magnetic atom, and so there's an interaction between the magnetic state of the electrons, the spin of the electron, and the magnetic atom of cobalt. That's discussed in much more detail in Feide and Heller's paper. So if that's of interest to you, you have to go and actually read their very nice theoretical understanding of this. Okay. If you like to see simulations on the web, I was looking around this summer and I actually found a web page that allows you to simulate these quantum corrals. So if you go to that web page, you can watch how these things develop right before your eyes. So I think I'm about done summarizing scanning tunneling microscopy, and I'd like to summarize. Right? We had to go very quick. I tried to hit the high points. I tried not to tell too many lies so that you have a sense of what's important and what's not. And what you realize after you do this scanning tunneling microscopy for a number of years is that to really do it well, you need very flat substrates. They have to be electrically conducting, and they have to be well characterized. So they can't be changing as you do the experiment. They have to be reasonably stable. That's what I mean by well characterized. The best experiments are done in ultra-high vacuum and at low temperatures. If you do not have UHV and low temperature STM, you're probably not competitive with the best groups in the world. The experiments require lots of time and money. The equipment is not cheap. It's $1 million plus to build nowadays. And it often takes 4 or 5 years just to custom build an STM chamber to do a certain type of experiment. You really need a lot of infrastructure to make these experiments work, so you need a group. You need an extended group of students and postdocs that stay with the lab for long periods of time, right? Because the tricks that are learned have to be passed on to the newer students. And if you're constantly losing students and not maintaining them, it's really tough to do these state-of-the-art measurements. And then lastly, you really need some good theoretical support, because ultimately you have to be able to do these density of states calculations to compare theory with experiment. So if you're not working with a talented theorist or talented theoretical group, it's tough now. Right? In the early days it was okay, but now it's a different ballgame. So that gets us to about 1986 in the timeline. So we've gone from like 1981 to 1986, five lectures. If you come to the next lecture, we're going to start to talk about the transition from STM to AFM. All right, so I'm just going to give a little historical perspective. Having lived through that period, I can talk about what it was like. I'll give a little historical perspective on Thursday's lecture. And then I will turn the floor over to my esteemed colleague, who will tell you everything you need to know about AFMs. So that's all I have for today. Okay.